Okay, so I think we can start with our webinar. So hope you can see me. My name Reiner Zitzmann from CANopen. So I'm managing the office in Nuremberg from CANopen GmbH, and I represent CANopen on events, fairs, and also in international standardization. So, for example, in the IEC TC69 WG10, I'm the project leader with regard to CANopen communication. I have standardized together with a lot of other experts in the IEC TC9 WG43 CANopen on a vehicle bus level in rail vehicles. And finally, I combined the standardization of CANopen in garbage truck applications, truck-mounted garbage truck applications. So in the TC183 WG3. So CANopen GmbH is a 100% daughter company from the association. So the CANopen Association has been founded to support the usage of CAN, to arise awareness of CAN communication, to assist people in using CAN. And we're doing this since 1992. And therefore, we have established a huge social network. And if you are using CAN, so you're facing maybe some challenges, then one idea could be to come to CANopen, to contact us, and maybe we can assist you directly. Nevertheless, we can always rely on our big social network that we have established since 1992. So in this social network, there is typically someone who is focused on solving such kind of issues that you are facing, and we can establish a contact to this party, and you can overcome your challenges quite easily. So it's good that you have this association. It's a neutral association. We have not a big company in the background, and therefore it's no problem to contact us, and we appreciate assisting you. Who is CANopen? Where we are located? CANopen is in the south part of Germany, in Bavaria. We are directly located in Nuremberg, in the city center. So typically in non-corona times, it's rather easy to contact CANopen, to come to us and to discuss your issues, your challenges. Now it's a little bit more tricky with corona, but nevertheless you can contact us by email, in our social media, or just give us a phone call. Briefly to the history of CANopen. As I've already said, CANopen has been funded in 1992. You see here the funding members, and we want to raise awareness of CAN-based networking, that you say, well, we have there such a medium that is reliable, robust, rather simple to use, highly available from a lot of different sources. So this makes CAN attractive, and this we are going to tell the people and how to use the CAN. Furthermore, CANopen serves as a neutral base for developing specifications. So if you have a project where several companies develop devices, and these devices have to meet at the end of the day in the very same network, then it could be a good option to say, well, just rely on a CANopen specification. Maybe there is already one for this task. So it's rather simple. You have a shortcut in your development, and you can say, okay, there's no need to negotiate with all the project partners. We can just say, we are using this, what is already has already been negotiated and determined by CANopen, or you can come to CANopen, use this neutral ground, and develop a corresponding specification for your kind of application. What we see on the slide as well, when we are looking on the CANopen history, that in the last green lines we see that the history of CAN has not been written yet. So we are still writing on the history. So on occasion of an international CAN conference organized by CANopen, Bosch has presented in 2012 the CAN FD, CAN with flexible data rate. And based on this, we have developed CANopen FD. So this CAN-FD is now coming to the non-automotive market, and therefore it is also a good idea to update CANopen with regards to CAN-FD to make usage of the benefits of CAN-FD. And these tasks, well, we have a first version, but these tasks finally are not finalized yet. So we have still some job to do. And if you are interested in these things, then as CAN Automation member, it's all the time very easy to take part in these meetings. And on the other hand, also as a guest, it's a possibility to come to these meetings and to have a look what's going on in this topic. And in the very last line, you see we are still working on some improvements on CAN. So in December 2018, a first working group has met to define a more performant CAN, the CAN XL, and these tasks are also ongoing in CAN Automation Association. So CAN Automation is a members-based association. We started in 1992 with about 16 members. At the moment, we have roughly, I think, 718 member companies. So at the beginning of the year, we had 670 members. So although that embedded communication is no longer the big topic in the fairs and the conferences, we can see that there's still a need for having such an association, such as CAN Automation is, as we have such many companies that say, well, it's for us a benefit being in this association, being part of this social network offered by CAN Automation. So what is CAN Automation doing? On the one hand, we assist you in some marketing activities. We try to open some markets. Therefore, we go to relevant fairs, conferences, present what's going on in the CAN market. Why is it important, or why is it a good idea to use a CAN-based solution in a specific application field? We have therefore several active marketing groups for CANopen FD, for example, for CANopen in the usage in elevator control, lift control, or for the usage of CANopen in garbage trucks. So, of course, we had also some others. If you think in your application field would be good if we are doing some marketing, then we can also open there a kind of marketing group and emphasize our marketing activities in this group. We have also a technical working group. This technical working group is a technical committee, and this coordinates the sub-layered activities. So we have there, for example, an interest group CANopen that maintains a CANopen document and all the relevant tasks with regard to CANopen. We have the same now for CANopen FD. How can we update CANopen in a way that we can make use of the benefits provided by CAN-FD from the stage of a higher layer protocol, such as CANopen, so it's the updated CANopen FD. We have also installed a similar group doing the same for J9039, mainly now accompanying the mapping of J9039 to CAN-FD at SAE, and also developing some own documents. So if we support several higher layer protocols, it does not make sense to change the application description of a certain device depending on the communication interface. So we see this is independent, and therefore we have a working group IG Profiles that describes the organization of data from I/O modules, drives, sensors, and so on. So from a specific device class, and then these parameters can be mapped to the used communication medium, such as CANopen, J9039, or whatever. Furthermore, all these high layer protocols are intended to be mapped to a CAN data link layer and physical layer. So we have therefore a working group lower layers that is dealing now with developments in these communication layers with regard to the ISO OC 7-layer model. So we have in this interest group, on the one hand, a working group that is developing CAN XL, so under patronage of the SIG CAN XL. A lot of companies meet and evaluate how can we improve the CAN-FD communication furthermore. There's another working group that deals with signal improvement. How can we achieve a good signal level in our CAN network so that we can deviate from the line topology and can nevertheless communicate in a good way. And finally, we have an interest group safety security. Mainly they are dealing with these subjects, but it's a little bit difficult to find a common denominator when you say, okay, we want to have a common safety solution, a common security solution. Nevertheless, they have now a working subject. It's more in the direction of availability, increasing the availability of an application. They are at the moment funding a working group working on a redundancy concept for CAN-based communication, independent of the high layer protocol that you're using. So you see, a lot of services are offered from CAN in automation with regards to the development of specifications. Then, depending on this, we do some technical work. We try to explain people that there's a new CS specification. We try to introduce to the specification by seminars, in-house seminars, consultancy services, and for some profiles, we can also offer testing services like conformance testing or interoperability testing. And on the other hand, we have to raise awareness by our media, for example, the CAN newsletter, which informs on latest developments in the application field of CAN. We have product guides where you can see some CAN-based products, or we explain why it is reasonable to use a CAN-based solution in a certain application field. When we go to fairs, we provide some brochures explaining the advantages and benefits of using CAN in this kind of application field. We organize also our own conference. It's the International CAN Conference that should have been the last one in March in this year. Due to the impact of the occurrence of coronavirus, we had to postpone this, and we hope now that we can have this meeting of CAN experts in June 15th and 16th next year in Baden-Baden. Finally, we'll decide on this subject in December 18th in Nuremberg, on occasion of the business committee meeting. So we hope that we can re-establish this meeting of CAN experts where they can network, can exchange their experiences here in the International CAN Conference format. But we are not sure yet whether we can do it in a pure online format or whether we can have, once again, face-to-face meeting here. Yeah, in general, we have also our publications which can inform you on relevant developments in the CAN field. On the other hand, this may be also a good option here to present yourself as CAN experts or to do some advertisement. And finally, if you think everything what I've shown to you is interesting, then please feel free to become CAN Automation member, use full access to the documents, and be part of the social network provided by CAN in automation. So, coming to the subject, migration from CAN to CAN-FD. So, why is it a subject? We have seen that CAN-FD, CAN with flexible data rate, is now available in the cars. The first car using CAN-FD is now available on the street. It's the cars from Volkswagen, the Golf Neo, the Golf 8, implementing 5 or 3 CAN-FD networks. And Volkswagen is not the only automotive car manufacturer. We have other car manufacturers that are also using CAN-FD in their cars, and we can assess that in midterm in the automotive industry, CAN-FD will substitute classical CAN. And this means CAN-FD will be available in the same format and in the same numbers and with the same attributes as classical CAN today. And therefore, it makes sense to think about CAN-FD and how can we migrate from a classical CAN-based solution to a CAN-FD-based solution. Therefore, it makes sense to have an eye on CAN-FD. Let's remind us a little bit how does CAN-FD look like. So CAN-FD is an abbreviation for CAN with flexible data rate. And when CANFD had been introduced, the engineers at Bosch thought, okay, how can we improve the classical CAN and how can we accelerate the classical CAN? And one attribute that the engineers from Bosch wanted to keep was the simplicity of CAN. In classical CAN, you don't have to think too much on network design or system design. You just configure those CAN telegrams that you want to transmit in your CAN device, and then you add your device to the CAN-based network, and then depending on the CAN identifier's priority, the CAN frames range into the data flow in your network. So it's rather simple, but this simplicity is based on something that is called an in-bit time response. You write your CAN identifier on the bus, and then in the bit time, you get the response whether you have the highest priority and you're allowed to send, or whether you have to go into a listening mode and there exists another high prior device in the network sending a high prior message, then your message, and then you have to wait and can try afterwards. This mechanism is responsible for this indirect dependency between data rate and maximum network extension, and it limits our CAN-based network in the classical format to 1 Mbit. But as soon as this negotiation, who is allowed to send, is over, then we are entering a kind of streaming phase, and we can open up our communication speed to what our physical layer is capable to drive. So you see here, we have here played around in a laboratory condition with a classical CAN network, and if we communicate CANFD, then we succeeded in transmitting up to 15 Mbit in the data phase. So as soon as we are in the streaming phase, we can open up the communication speed to what the physical layer is capable to drive. Don't take this 15 Mbit too serious. Of course, your applications are not necessarily always under laboratory conditions, but they have to withstand a bigger temperature range. So let's have a look on the ISO specifications. What are considerable communication speeds? At the moment, you find their operating limits for 2 Mbit and 5 Mbit, so those are more realistic values than these 15 Mbit. But this shall just show you the basic principle of CAN with a flexible data rate. You start, or you may start with a nominal communication speed, as you know from classical CAN, and then the data part of the frame you transmit with an increased speed, and then for the acknowledgement, once again, we have an in-bit time response, and then we communicate again with a nominal speed that we have used at the beginning. So CANFD allows you to transmit one CAN frame with 2 communication speeds, and all the network participants have to know in advance both bit timing settings for these communication speeds. So to increase the efficiency, we can increase the number of accelerated bits. So it means we can enlarge the data field. You see a comparison between the classical CAN-based CAN frame and the CANFD-based CAN frame format, and we'll see apparently they look identical. You have the same bit fields, the same bit field naming, but we differ here a bit in the size. So we have here in the data transmission phase the possibility to transmit a data field from up to 64 bytes of data. All the rest is more or less identical. As I said, some bit fields are differing, like the CRC. You need a more increased CRC to secure this CANFD frame format, and you have additional control bits here to indicate the size of the data field. We have seen we have 2 attributes in CANFD that allow us a higher data throughput. We have on the one hand the size of the data field, on the other hand the transmission speed, and we can control them independently from each other. So in the International CAN Conference from 2012, Florian Hartwig from Bosch has shown what can we achieve with CANFD, and he made a small demonstration. he said, okay, if we communicate with 500 kilobit, of course, we have an average bit rate of 500 kilobit. You're communicating an 8-byte frame. And now, if we increase the communication speed in the data phase up to 4 Mbit, then we achieve an average communication speed of 1.4 Mbit. So this means if you use a data field that is similar to today's classical CAN data fields, and you are increasing the speed, you can already gain some kind of data throughput. This we should remind ourselves, because this could be interesting if we say for in kind of a migration path, we map a classical higher layer protocol on a CAN FD controller. So for the higher layer protocol, it simply does not matter which kind of data link layer is lying under this higher layer protocol. They are just using an 8-byte data field in case of doubt. And if you are here doing some bitrate switching, then you can already achieve something with regard to the data throughput. But if you want to use the full power of CAN FD, then you should also increase the data field, and this we can do as well. So we see here in this presentation from Florian Hartwig up to 64 bytes. This is the limit of the CAN FD frame, and then we reach an average speed in this experiment of about 3 Mbit. So you see we have two different attributes, the speed and the size of the data field, that we can now use for CAN FD networking and to increase the data throughput to meet security and safety challenges, because we need there this lengthened bit field and so on. Let's have a rush through the details. So how does the CAN FD frame look like? So the arbitration field is more or less identical. I just do not have a RTR bit, it's a reserved bit. CAN FD does not support the remote frame format. Then we have the control field. The control field is a little bit extended. On the one hand, we have there the FDF bit, FD frame format bit. The FDF frame format bit indicates are we in the classical frame format, then we have a dominant reserved bit, or if it's recessive, then we know we are this CAN FD frame format. Then there's a new reserved bit for future extensions. This will be used for CAN XL. And then we have this bitrate switch bit, and if this is recessive, then we are switching to the accelerated communication speed in the transmission phase. So this means I have here a switch bit, and depending on the state of the bit, we run with the very same communication speed, or we switch over to the accelerated one. This is very important with regards to migration passes. So for example, the communication speed has a big impact, of course, on the topology that I can use in my network. And the higher the speed, the more critical it may get that I can use or reuse already existing topologies. But if I do not have any issues in data throughput, I can also say, okay, I do not do the bitrate switch, and anyway, I just need a 10th, a 12th byte, and that's it. So I don't have any issues also in latency either. So why switching? Why doing here some trouble maybe with regards to existing topologies? Just use or stay with the existing bitrate, with the nominal one, and run through with one single bitrate and solve your safety, security issues, maybe by adding an authentication checksum to your data in the data field with a 12 byte, and that's it. And then you have solved your issues with CAN FD. Or if you want if you say, okay, I want to reduce the latencies if my frames are a little bit longer, then just do a small switch with the bitrate switching. Maybe you use today 250K, you say, okay, I'm switching to 1 Mbit, and that's just a small switch, but I've reduced the latencies and I can communicate all the data I need without any big impacts on the topology. Furthermore, we have here an AC bit. The AC bit is an error state indicator indicating the error state of the transmitter. I'm either an error active or error passive, and we have remaining 4 bits for indicating the size of the data field. And this means if we have still our 4-bit, we need a real coding, and we cannot extend the data field smoothly byte by byte, but we can also only extend it in certain steps from 12 to 64 bytes. This we have to consider if we are using lengths and frames. Maybe if we want to transmit 17 bytes, then we see, okay, at least we will transmit 20 bytes, and we have to deal with some padding bytes to fill up the CAN frame with defined data and not just rubbish that is occasionally in my memories. The entire frames are secured with a CRC checksum. So depending on the size of the CAN FD frame, different checksum will be used. For all frames up to 16 bytes, the 17-bit checksum is used. For all larger bytes, the 21 CRC checksum is used. And we see here, this is the CRC field. And I want to emphasize here especially this staff count field. The staff count field had been invented during the standardization process of CAN-FD at ISO. And there exist already on the market early bird implementations that had not been aware of the staff count field. They are called so-called non-ISO CAN-FD implementations. And you can use them for communicating classical CAN, and you can use them for play around with CAN-FD. But the end result from ISO standardization is that one, what you're seeing here with the staff count. And as this is then a format change to those early implementations, the ISO implementations or the implementations according to the ISO standard and the early ones are incompatible because of this frame format change. So if you want to see, do we have already in our devices CAN-FD? Yes, then make sure that staff count is supported by this CAN-FD controller, and then you can assess, is this a new ISO implementation or is this a very early bird implementation, a so-called non-ISO CAN-FD implementation, so that you can assess what about the interoperability. So all the rest remained equal, let's say. You have the error frames, you have the overload frames, and if you do the bitrate switch, you switch at the sample point of the BRS bit to the accelerated bit, and at the CRC delimiter, you are switching back to the nominal speed, and the acknowledge field and all the rest is communicated in the nominal speed. As soon as you detect an error, your device will send out an error frame, switch back to the nominal speed, and do the error handling also in the nominal speed. So we see here we have also, according to ISO, that is standardizing CAN-FD, the ISO 11898-1 from the year 2015, 3 implementation options. So we see here we can support in classical CAN, we can support classical CAN and tolerate CAN-FD, and we can support both. Last one is recommended for all new implementations, but we can see anyway all CAN-FD controllers can communicate classical CAN. Nevertheless, we have to think about that there exists a configuration option that I can say I allow only the CAN-FD communication, but this is just a configuration option. Also, those implementations have to support classical CAN. This means I can always communicate with classical CAN in my network independently which kind of CAN controller I have implemented and I am using in my network. On the other hand, as soon as I communicate CAN-FD, only those where CAN-FD is activated and that are using CAN-FD, only those can then communicate. All the others will drop out. The classical CAN controllers will go into an error handling, and the CAN-FD tolerant, they won't go into an error handling, but at least they cannot take part in the CAN-FD communication. This we have to know. Furthermore, we have to think about the availability. CAN-FD is now available in IP cores, in microcontrollers, transceivers are available. Also, protocol stacks for higher layer protocols that have been adapted, such as CANopen FD, they are available. CANFD board level products are available and tools. So this means we can really start with CANFD. There exist also implementation guidelines, implementation hints, also available from CAN Automation. Here I like to emphasize also the -4 document from the 601 series that is available for purchase at the CAN Automation. So it's a document dealing with signal improvement, ringing suppression. So this means typically a CAN-based network should follow a line topology, but if I cannot implement a line topology, as the topology is typically not determined by the system designer, but by other design aspects or by the application, then we have introduced by the design of our network already some ringing, some noise in my network, and to calm down this ringing and to allow a proper communication, there exist special transceivers that support signal improvement or ringing suppression, and those transceivers are described in the document CA 601-4. So I like to recommend you to have a look to this document and to see what is defined there and how does it work, so that you can run in your today's network topologies a CANFD, maybe with a little bit increased speed. If you are dealing with long-term applications, then you may face several protocol versions. And in this following two slides, I just like to sum up which kind of protocol versions may be out in the field and you may face. So this may cause some troubles with regards to interoperability aspects. Early bird implementations from CAN had been implementations that were only able to communicate with 11-bit identifier, formerly known as CAN 2.A. So we have furthermore the 2.B passive CAN controllers that were able to communicate with 11-bit identifier, but were just able to tolerate the extended frame format. And since 2003, all new CAN controllers have the obligation to support both the base frame format and the extended frame format, the 11-bit identifier and the 29-bit identifier. And to this, we're adding now the CANFD frame format, the new CAN controllers. They can add the functionality to communicate the CANFD frame format or just to tolerate the CANFD frame format compliant to the ISO 11898-1 from the year 2015. So in addition to this, we have the ISO and the non-ISO CANFD frame format. So we have heard during the CANFD standardization, there had been some changes in the frame format, and the early bird implementations had been already ready then and had been already sold in several projects, so you can meet them also in the market. And this means, once again, that CANFD implementations may be incompatible with other CANFD implementations if you have ISO and non-ISO CANFD in the very same network. So I summarized this in this small table here. Classical CAN communication is always no issue. Extended frame communication should also be no problem. If you're using CANFD implementations according to the ISO, what is definitely the mass market, and all the automotive car manufacturers, they order only ISO CANFD frame format compatible CAN controllers. So this will be the mass market. And here you have to have ISO CANFD implemented CAN controllers to communicate ISO CANFD frames. And if you have early bird implementations, and if you want to use this, then make sure that only non-ISO CANFD compliant CAN controllers are in your network. How can we now achieve that we can migrate CANFD in our application? And here I have provided you with some drawings. So what will happen if you have a mixture of classical CAN-based devices and CAN-FD-based devices in the same network? So we see this here. As long as we are using classical CAN, then there's no problem. We have absolute data consistency. As soon as we use in such a system CAN-FD communication, then the classical CAN-based devices will get into trouble and will destroy the communication by means of error frames. And some of these classical CAN devices will drop out, will drop out into the bus off state. So this is not possible. This will not work. There exist now solutions to make something like that work. So there exist specific measures that you can take to protect classical CAN-based devices from seeing CAN-FD-based communication. So these measures, we see here two examples. The one is the CAN-FD shield transceiver from NXP. It translates incoming CAN-FD frames into some receive errors, reception errors. So you will increase here at the backline classical CAN controller the receive error counter, and they will remove the error handling to the bus. There will be not an error handling to the bus. So I just protect here my backline CAN controller from seeing CAN-FD. In the worst case, this classical CAN controller will turn into the error passive state, and as soon as there is, once again, classical CAN communication, the CAN controller will switch back into the error active state and can communicate. A similar concept has been presented by company Quasar. They have something that is called the CAN-FD bridge, and they translate the incoming CAN-FD frame into an overload frame, into a classical CAN frame from the length 0, and to make the timing matching, they're working with overload frames, and so they avoid that the backline CAN controller is turning into an error state, into error passive state. It remains in error active if it had been there in advance, and you can also protect with this measure your backline classical CAN controller from seeing CAN-FD frames. But always you have to do some soldering, remove the existing CAN transceiver, put a new CAN transceiver inside with these features. So sometimes you do not have access to the printed circuit board to do such changes. It may be simpler doing something like that. To use a simple bridge, they exist already on the market, a bridge interpreting between classical CAN and CAN-FD. So if you use frames that are not larger than 8 bytes, it's a rather simple forwarding from the left side to the right side and back. If you communicate larger frames on the CAN-FD side, then you have to put some logic on this bridge. You have to implement here some routing functionality that breaks up the big frame into several pieces and communicate then these up to 8 byte pieces in the classical CAN-based side. So something like that we have already considered in CANopen, not with special regard to CAN-FD, but we can reuse it for CAN-FD. We have, for example, configurable network components specified in the document CR456, and we can very easily implement here a CAN message forwarding, so that you just say, okay, the incoming messages on port 1 shall be mapped to port 2, for example, if they are in this index range, and to these or that CAN identifier. So something like that will work rather easily, as already described in the document 456. The other problem is how can we deal with length and frames supporting up to 64 bytes. Then we need to put some additional logic how to break up these 64 bytes into several pieces. Also here we have already a document, and we have already commercially available stacks from different sources implementing CR302-7. We have here this bridging functionality where you can break up this length and frames, map it to a shared memory, and from this shared data pool you can very easily communicate the pieces here, in this case with the means of CANopen, to other network sites and communicate the relevant data. So we see here the shared memory provides us with a big table of slots where you can store your received data, maybe from the CANFD side, and make it available to CAN side. So what we are doing with this measure is, for example, using the same application layer, CANopen, on the classical CAN side as well as on the CANFD side. So we can do here a simple message forwarding. We have seen how can we handle length and process data objects of up to 64 bytes. This would be able to handle with this document 302-7 rather simple. Also, something like that is already important. How can I do diagnostic accesses, configuration accesses from one side to the other one? On the one hand, I can use this shared memory, provide there the relevant data, and access from the both sides with a corresponding communication medium, maybe via the service data object as we know it from CANopen. Sorry. Or what we can also do is we can, using the direct access, we have an SDO remote indication in CANopen 302-7. So as soon as we know the topology, we can directly access through such a gateway application the other side and all attributes in this device, and can configure the device according to our needs. Here we see very briefly how this works. I just indicate to my gateway device, hey, I want to speak to this network and there to this node. So as I say, I need to indicate the topology, and then the gateway confirms yes, and all the further transfers will go to this device on the other side. And this we can use very simply, as it is highlighted there. So summing up, one transmission or migration path could be that I'm using the same higher layer protocol. In this slide, this is now an example used CANopen, the same higher layer protocol all over the application. I have a full transparent application layer, and we just don't care that it is one time based on classical CAN, another time based on CANFD. And we have seen on the very beginning, we can already benefit from CANFD if we are using data fields that are not larger than 8 bytes, but we accelerate the communication speed, then we can increase already the data throughput. And here, from a higher layer protocol point of view, I just don't care whether the data has arrived via classical CAN-based frames or CANFD frames. But of course, I'm limited here a little bit by the protocol stack. Maybe I want to use an lengthened data field up to 64 bytes, and therefore I want to use something, a higher layer protocol that is optimized for CANFD. And this could be, as an example, here CANopen FD, and then I can use here the full power of CANFD on this side. Therefore, let's have a very brief look on CANopen FD. How does it work? It had been released in 2017. Devices are available, first protocol stacks are available from different sources. And what we are doing here, we're mapping an optimized higher layer protocol, CANopen FD, to the CANFD data frames. So if you have already some glue about CANopen, then you see, okay, not all the services available in CANopen are limited by the classical CAN frames. And when we extended CANopen with regard to CANopen FD, we said, well, we want to achieve that today's CANopen user can maintain most of its knowledge and its experiences also in a CANopen FD-based system, and we only want to make changes in this part where we can really benefit from CANFD, and this is in these protocols that are limited by the classical CAN frame. So these are the transport-oriented protocols like PDO, SDO, and if you want, also the emergency. Let's have a brief rush through these protocols. We see CANopen PDO is determined by a so-called mapping table. It's a linking to a device internal database, and from there I map up to 8 bytes of data into a classical CAN frame. Now we have 64 bytes, so the only thing that we have to do the threshold value for this linking table, how many data can I map to a CAN frame, is now extended from 8 bytes to 64 bytes. That's it. And this was the only thing we had to do with a PDO. From a formal description point, there was no need to change anything. The emergency, well, we have updated. We have now a more comprehensive error information. So we have now a timestamp. We have some status indication about the type of the error event. We have also, for more complex devices, the possibility to indicate which parts of the device got into trouble. And furthermore, we have a renewed error history where we can store all the error events that are upcoming in the CANopen application. And furthermore, we tried to update the SDO. With the SDO, we had the problem that it was rather tricky to update. And then we did a deeper analysis on the SDO, and then we said, well, we need some new features, some additional features, and therefore let's remove the classical SDO and let's introduce something new, the universal service data object, or briefly the USDO. The USDO has a full function coverage of the classical SDO, but in addition to this, it allows dynamic communication channel establishment during system runtime. We can have a multicast or broadcast communication. It has a simplified block transfer. We can have parallel access between several devices, and furthermore, we have updated abort codes that allow a more closer error description. I just want to show you simply how it works. So the USDO had been assigned having byte alignment in mind. So it's also very easy to implement, not longer this dealing with these bit patterns, as you know, maybe from classical CANopen. And we see here we have a destination description, and this can be can alternate during system runtime, of course. Therefore, I have very easy possibility from any device to contact any other devices. We describe our data. We can have several transactions identified by the session number. So this is a way how CANopen is now introducing new functionality by updating CANopen with regards to CANopen FD. If you want to hear more about this, we will have next time a CANopen FD webinar, and I will go into depth. And what we can see with this new functionality, we can use this, for example, for accelerated firmware update during end-of-line production. We can check with several requests in parallel what is the status of my firmware update. We can simplify applications like that, where we say, okay, we have hundreds of drives doing exactly the same. If I want to configure in classic CANopen, this had been in maximum 127 SDO connections, and one by one I had to configure. Here it's one USDO communication, and I can configure all the devices in parallel, and this saves time enormously. Also, the time of static CANopen and CAN-based networks is over. So, for example, more and more the end user, who is neither a CANopen expert nor an expert in the system design of a certain application, is doing changes in the system. So, for example, in a Pedelec, where you have typically CANopen communication inside for doing the energy management, you add as an end user batteries, displays, whatever, and then you don't want to configure here any communication channels, and functionalities like provided by the CANopen FD USDO provide now these communication channels that have a dynamic cross-communication between the devices. Also very beneficial, for example, for IoT applications, that you can have just-in-time communication access to the data points that you're really requiring. And also for this CANopen FD, everything is available, protocol stacks from several companies, first devices, even gateway implementations, moderating between CANopen and CANopen FD. Company EMSA is there currently developing something, preparing something for coming to the market. And they're dealing also with such subject that you have now a more powerful USDO in comparison to the classical SDO, and they have to deal with this, that one USDO access may end up in several SDO accesses, something like that. They are solving in their devices. But with regard to our subject, we see also such migration paths exist that I have a classical CANopen side on the one hand, on the other side a CANopen FD side, and there are devices available on the market that can moderate between these both sides. CANopen is not the only higher layer protocol that has been updated with regard to CANopen FD. There exist other ones such as J9039. This is currently under development at the SAE, and some further higher protocols had been updated. So similar migration paths as I've showed for classical CAN to CAN FD via CANopen FD are available, of course, in other higher layer protocols and other environments. So I hope this had been beneficial for you. This webinar brought you some interesting insights. So summing up, the CAN FD controllers are going to substitute classical CAN. CAN FD is now used more and more in modern cards. So we can assume that CAN FD will be available in future. Also, if you are going into your laboratory and you evaluate which kind of CAN controllers are using, maybe you get a surprise that you are already using CAN controllers for the purpose of communicating classical CAN. But if you do an analysis of the data sheet, you may see, oh, they are already capable to communicate CAN FD. Maybe. I have several times experienced something like that. And if CAN FD is already on board, why not using it? If you get more or less free of charge this added value, then you can offer it maybe to your customers. And then it's rather simple to switch over to adapted higher layer protocols like CANopen FD. The migration path, as I have already shown, could be in that way that you map a classical designed higher layer protocol on the CAN FD controller. You can already win data throughput by increasing the communication speed in the data link layer. For the higher layer protocol, it doesn't matter simply. And if you want to use full impact of CAN FD, then you have to use the adapted higher layer protocol such as CANopen FD. Products with regard to CANopen, for example, they are available. Bridges, routers, gateways. Also on the lower layers, CAN FD bridges are available from several sources. So from this aspect, you can start with the migration and you can start with CAN FD device design. If you want to be kept informed, on the one hand, please consider our info mail or members news. Follow us on our social medias. So there we regularly report on latest movements, developments in the application field of CAN, what's going on in the CAN in Automation Association. Normally, I would say, please feel free to visit us on the fairs and the trade shows. Unfortunately, due to Corona, lots of them have been cancelled or we were not able to attend. So this year we won't show up at any trade show anymore. But I hope next year, when the whole Corona situation hopefully calms down, then I would like to invite you to our booths on various trade shows. So you will be kept informed on our website on which kind of trade shows we are taking part. As also conferences had been cancelled, we have now several online technology days. So if you like, please show up. We have the different topics there with regard to elevators, with regard to special purpose cars, commercial vehicles. And if you have some Chinese colleagues, then you can also link them to our technology day in Chinese, where we give a short look up on the status of CAN-based networking. With our series of SIA webinars, we will continue on the 14th of October with a deep insight with regard to CANopen FD. And I would appreciate if we would meet on those events again, and if you stay interested in CAN-based networking. So thank you very much. Much success with your CAN-based projects, and I hope we can meet again. Thank you. Bye.